Hello, this time we'll see if we can apply the same type of analysis techniques to work out what happens when we try and charge capacitors up. So this is the circuit that we're looking at now. We have a voltage source here, which is going to be connected through a resistor to a capacitor when the switch is closed. This is a constant voltage source. What happens? Well, it's just nodal analysis again. We can apply our usual Ohm's law and Kirchhoff's law techniques and determine that after the switch is closed, I'll have a voltage V0, a constant voltage V0 at this point in the circuit here, and then a resistor here, and then we're going to be going through a capacitor down to ground. I'll define the voltage at this bottom node of my circuit as my local reference voltage of 0. And I want to know the value of the voltage across the capacitor. This point here, I'll call it V of t. Right. Well, I'm going to have a current flowing through this resistor in that direction. And the current is going to be V0 minus V of t, that's the voltage across this resistor, divided by the value of the resistor itself. It's going to be a function of time because this voltage here is a function of time, so the voltage across the resistor is going to keep changing. But this is also the current that flows onto the capacitor. Therefore, it's also equal to C times dV dt. So now I have this differential equation to solve. And I can proceed in exactly the same way. dt over CR is equal to d V of t over V0 minus V of t. And the next thing I'm going to do is multiply both sides by -1. Because if I do that, I can write this right-hand side in this format, and notice that the differential of the bottom of this fraction is equal to what's on the top. If I differentiated that with respect to time, I would just get that, dV dt. Therefore, I can integrate this and just get a logarithm again. This time, it would give me the logarithm of whatever's on the bottom, V of t minus V0. Now, the limits of integration on this side, time starts off at 0 and ends up at some time of interest t. The voltage on this side starts off as 0, because immediately after we close the switch, there would be no charge on the capacitor, no current has flowed onto it yet, so V of t would start off as 0. And it would head up to some value V after a particular time of interest. So I would get this. That is log of V of t minus V0 minus the log of 0 minus V0. And once again, I can use the trick that the difference in two logarithms, log of x minus log of y is log of x over y, and write this as the log of V of t minus V0 divided by minus V0. Which makes more sense if I multiply top and bottom by -1, V0 minus V of t over V0. And that must be equal to the integral of this side, and that would just give me minus t over CR. Take the antilog of both sides and multiply up by V0, and this time I would end up with V0 minus V of t is equal to V0 times e to the power of minus t over CR. Bring this over here and bring this over here and do a bit of fiddling around, and that would end up with V of t equals V0 1 minus e to the minus t over CR. Final result. What does that look like? Well, when t is 0, then e to the power of 0 is just equal to 1, so v of t would start off as v0 times 1 minus 1, which is 0. V of t would start out at 0. And as time increases, e to the power of minus t over CR would get smaller and smaller and smaller and smaller. So 1 minus this would get closer and closer and closer to 1, which means that v of t would get closer to v0 as time goes on. And if we plot the graph, we end up with this, which you'll get very familiar with because it comes up time and time again in the analysis of time-varying circuits. It's an exponential charging curve. Once again, we often characterize these in terms of the time constant. The time constant, in this case, RC, again, just like it was in the discharge. And this time, the useful figure to bear in mind is 63.2. After one time constant, we've got to 63.2% of the full charge. But you'll notice the capacitor never gets completely charged. It would take an infinite time for the voltage across the capacitor to actually get to V0, where V0 is the voltage of the voltage source. Okay, that's all for capacitors for now. Next time we'll have a look at inductors.